Hello everyone. Today I'll discuss about molecule Propofol, a very simple molecule, but it has a very important application. This is the chemical structure of the molecule. You can see it is nothing but 2,6-diisopropyl phenol. Very simple molecule. This molecule is used as an anesthetic during surgery. This molecule was discovered by John B. Glenn in 1973. However, the molecule got US FDA approval in 1989. Today, I will be discussing about commercial manufacturing process of this molecule. There are several reports available. However, I will be discussing about a particular report. As per the earlier reports, the molecule can be synthesized from phenol. The alkylation can be done by using propylene gas in presence of Lewis acid catalyst under high temperature and high pressure condition. However, the process includes some difficulty like possibility of over alkylation. So the target molecule contains alkyl group at the 2 and 6 position, but in this process it will give some quantity of 2,4,6 tripropyl group as well. So purification of the molecule was challenging. That's why in modern days the synthesis procedure includes this method where the starting material is para-substituted phenol. So here, and also in presence of instead of using propylene gas as the isopropyl source, isopropanol can be used in presence of concentrated sulfuric acid for this alkylation reaction. Here the main advantage is as the para position of this phenolic group is blocked with carboxylic acid, so over alkylation is not possible. It is giving selectively alkylation at 2 position and 6 position. And after getting this molecule, base mediated decarboxylation will lead the final product formation. However, this process also contains some challenge, like as the first step reaction is getting conducted in sulfuric acid. So after reaction, neutralization is required using sodium hydroxide. In same way, second step reaction is getting performed in sodium hydroxide. It's a basic condition. So again, that base should be neutralized using hydrochloride. Now, these neutralization steps are usually exothermic reaction, as well as these steps include some safety challenges, and also use of this acid and base may lead formation of some unwanted impurity, as this molecule would be used for API purpose. So there is some limit for those impurities, like any impurity should be less than 0.05%. So that's why some more modifications was done by some other research group that I'm going to discuss in next slide. Here is the modified commercial route to synthesize the molecule, and it was developed by scientists from MQR Pharmaceuticals from Pune, India. They have started with the same raw material, para-hydroxybenzoic acid, and performed the reaction using isopropanol in presence of concentrated sulfuric acid. But once the reaction completed, they did not neutralize the reaction using any base. Instead, they poured that reaction mixture in cold water and extracted it with toluene, organic solvent. And then they evaporated completely the toluene and then precipitated the material using methanol water and got this material with 95% purity. Further, they did washing with cyclohexane and this material was obtained with 98% HPLC purity. After getting this molecule, they did sodium hydroxide mediated decarboxylation reaction under high temperature condition, and they have used 2-ethoxy-ethanol as the solvent for the reaction. Here also, once the reaction completed, they did not neutralize the reaction using any acid. Instead, they poured the reaction mixture in water and extracted with toluene, like the way they did in step 1. And with this extraction method, they got the final product, Propofol, crude material. And that material they purified further by high vacuum distillation. You can see the temperature they have used 80 to 90 Celsius at 0.05 mm pressure. And they got the molecule with more than 99.8% purity, HPLC purity. Now, they have collected some impurity structure from some previous literature, and they wanted to validate whether those impurities are present along with this synthesized molecule or not. For that purpose, they find out first some selective probable impurities. These are the structure compound 4, 5, 6, 7, 8. Now, as they wanted to validate these impurities, so they targeted to synthesize these molecules and then validating through HPLC. Now in next slide I will be discussing how they have synthesized these impurities. From the synthesized final molecule itself, they have synthesized 3 different probable impurities. Like compound 4, they have synthesized from this molecule using iron chloride followed by reduction with sodium borohydride. It's a homocoupling product. And this compound 5, you can see this is O alkylated product. They have synthesized by reaction of this compound with 2-bromopropane in presence of sodium hydroxide. It's a substitution reaction. And this compound 6, they synthesized by oxidizing this molecule using CAN. CAN is ceric ammonium nitrate. To synthesize those probable impurities 7 and 8, they started with this molecule. This is isopropyl substituted phenol molecule, monosubstituted. So first they have done MOM protection of this phenolic OH group, followed by the treated with N-butyl lithium and then boryl group introduction by using triethyl borate. Now after getting this intermediate 11, they have done oxidation reaction using acetic acid and hydrogen peroxide to get this phenolic intermediate 12. And here they have removed this MOM protection group using paratoluene sulfonic acid, and then that one was treated with acetone in presence of BF382 to get this compound 7. And to get compound 8, what they did from this intermediate 11, they performed one palladium catalyzed Suzuki reaction with 1-bromo-1-propene to get intermediate 14, and here the double bond was reduced by using hydrogen in presence of palladium charcoal to get this molecule. Now after getting these molecules, they have validated and they confirmed that these impurities were not present in the synthesized compound. Thanks.